Okay, so now let's talk about part number 2 of this exercise. And basically what I want to explain you is the how you can establish a water allocation system for, in this case, the first example is a river system. Later you're going to be thinking about a reservoir. So think about this. Think about that there might be a system with a river passing through different three water users, okay? And each user has a given water demand. In this case, the river has the highest priority. So what that means is that the river, well, if it is not naturally, the river will need to have some water flowing. And the amount of water for the river all the way down here it can be 2 units, well, from 0 to 2, and maybe more of the river keeping it here. User number 3, which is located in here, this user has a priority as the second priority. So once the river has taken its water demand, then user number 2 will start taking its water demand. How much? Up to 5 units of water here. Then we have users 1 and 2, and they have a priority number 3. What that means is that once the river and the user number 3 has taken their water demand, these guys will start taking the water demand. How much? User number 2, 2.5, and user number 1, 2.5, and user number 2, 3 units of water. So now, as we are seeing water coming in, I mean, we can actually see how much water can be distributed, and because we have eyes and we're doing all the math and figuring out how much water will be distributed first to the river, and then the second one to the user number 3, and so on. Now, in order for us to do something like this, then we will have to tell the computer how to do this. So in this case, what I'm going to do is show you how we can do this for the 4 users that we have in here. So let's start with the river. So think about how much water can we left. So water in here flows for environmental purposes. So in this case, what we have is that water in the river, how much water can flow in the river? So we can left in the river pretty much from 0 to 1 units. We can leave 2 units or a little bit more of 2 units. And it will be more than 2 units when all the users have already taken all their fair share. So now let's focus in here. When will the river in this part will only have a 0 or 1 unit in here? Well, that will happen if the water available, in this case Q in, is less than this amount for the river, okay, which is less than this Q river, or the water at demand, which we know is in this case this one is 2 units of water. So this will happen when Q in is less than 2. How much water will the river receive? In this case, it will receive only what is coming from upstream. So that will be how much water will receive in these conditions. When Q in is 0 or 1, the river will only receive that amount, and this happens when the water coming in is less than 2 units. Now, when the river will receive more than 2 units, the river will receive more than 2 units when this will happen when this Q in, so the water available, the water coming in, is greater than all of this. So greater than this Q river plus the sum of all the human water demands. So this is a summation. Basically, this summation, what this means is that it will be x1 plus x2 plus x3. That we know that these values are 5 plus 3 plus 2.5, and in this case is 10.5. This will be the numeric value, and water for the river, it will be 2. So when the flow coming in is, when Q in is greater than 12.5, that's the time when the river will start receiving more water. How much more water? Well, basically it will be, we can actually borrow it from here. So it will be Q, it will be Q in minus the sum of the human water demands. So think about this. So the amount of water that will be left in the river, it will be the water coming in minus all the water that has already been taken for the human water users. So when will it be something in the middle? So let me show you a little trick how you can figure that out. So this will happen, it will be to if this Q in, so I'm gonna put it in here, is rather than being less than 2, it will be when this Q in is greater than 2 units. But when this Q in is less than or equal than 12 units, 12.5 units, which in this case is this part in here. So what you're seeing here, or how I was able, it will receive only 2 units when, and again, this guy I put it in here, and then I change the sign, so I inverted the inequation. So when Q is greater than 2, but also when Q in is less or equal than, so when Q in is greater than 2, but Q in is less or equal than 12.5. So when this happens, the river will only be receiving 2 units of water. Okay, so this is how you can actually understand how in this case how we're gonna write these equations, so we can program this in a computer. So now let's talk about a user number. So first we have already done the water allocation system for the priority number 1. Now let's talk about priority number 2, which in this case is user number 3, which is here. So how much water can this user divert right in there? Okay, so in this case we're going to be doing something very similar as what we have done here. So remember that this user can take pretty much 0, or it can take its full amount, or something between 0 to 5. Okay, so let's start by evaluating how much, when it can be 0. So this can be 0 if the water available, so this water, this Q in, is less or equal than 2 units. So in this case, if this water coming in is less or equal than 2 units, only will be water will only be allocated for the highest priority user, which in this case is the river. When can this user can receive its full allocation? So that can happen if Q in, so the available water, is greater or equal than the prior priority, which it will be the river, plus 5. So when Q in is greater or equal than 2 plus 5, so when this is greater than 7, then this guy will always receive 5 units of water. when can it receive something in the middle? So that will happen when, and again, I'm just going to do this guy here in the middle. So Q in T. So when Q in is greater than 2, but is less than our guy here, which is Q river plus X3. So when Q in is less than 2, but also less than 7, that's when this will happen. How much water are we going to be allocating him? So basically when this happens, it will be Q in minus water for the river, which it will be and these values will be between 0 to 5. This will be only 0 and this will be 5. Okay, so remember that that's how we were able to do this. Now let's go to the last one or the two last ones, and in this case they are user number 1 and user number 2. So how much water in this case user 1 will be able to divert at that location, given that both of them they have priorities number 3. Okay, let's think about this and write some of the questions. So in this case, user number 1 again, it can receive 0, it can receive 2.5, or it can receive from 0 to 2.5. Okay, so when can it receive only 0? So it can receive 0 when, again, if the water available, and we've been always playing with this water available, Q in, is less or equal than what? Less or equal than 7. So when it is less than the amount needed for the river plus the amount needed for user number 3, which both of them they have higher priority, so that's when this will happen. Okay, that's when the user will only receive 0. When can it receive 2.5 units of water? Is the same when this Q in, so the available water is greater than the sum of all of this, greater than 12.5. So when this is greater or equal than the water for the river plus all the sums of the water for the human demands. So when this happens, when Q in is greater than 2 plus 5 plus 2.5 plus 3. So when this is greater than 12.5, then that's when it will receive 2.5 units of water. When can it receive something in the middle? So this will happen when, and again, I'm going to put here, this guy, this in equation, I'm going to invert it. So when Q in is, in this case, greater than Q river, so when the Q in is greater than 2, but it is less than 12.5, and 12.5 is this. So basically what you can see is this guy I put it in here, this guy I put it in here, and this guy I'm putting in here, as I've been doing in also in the previous one. So this guy I put it in here, this guy I put it in here. So when that happens, then it will receive from 0 to 2.5. So now we need to calculate how much water will be received by X1 when this situation happens. In this case, the first thing that we need to know is that it will receive this Q in, minus Q river plus X3. So any water in excess of 5, which is, excuse me, of 7, which is 2 for the river and 5 for the user. So when you have this water in excess, so Q in, so if you have 8 units and you have to subtract 7 because you need 2 for the river and 3 for the user number 3. So that excess of water, but remember that water will have to be, because they have the same priority, it will have to be divided in the same share. So if user 1 receives 20% of their allocation, user 2 will receive 20% of that allocation. Of user 1 receive 50% of that 2.5, user 2 has to receive 50% of 3 units of water. How can we estimate that share? Well, so basically it will be this amount times, and that's actually pretty simple. So in this case, it will be this x1t over x1t plus x2t. So as you can see, it's the proportion of 2.5 over 2.5 plus 3.5. So basically, this tells you what is the share that these two together can take water, and x1 it will receive that amount. It will receive it on that proportion of those two. Now let's actually think about the rest of the other users, which are excuse me, the last user, which in our case it will be user number 2. So in this case, user number 2, how much water will it receive? So it is pretty much extremely similar like this user number 1, okay? So it can receive 0 if exactly the same applies. The water coming in is less than the water for the river plus the water for user number 3, which both of them they have higher priority. It will receive 3 units if, again, the water coming in is greater or equal than the water for the river plus the human water demands for everyone. So when this value is greater than 12.5, when Q in is greater than 12.5, then this guy will receive 3 units. When Q in is less than, in this case is 7 units, and this is less than 7 units, then it will receive 0. When can it receive something in the middle? And again, we can do exactly the same. So we're going to put this guy in the middle, Q in. So when Q in is greater than this Q river plus X3, but is less or equal, less than, sorry. So when it's less than what we have in here. So basically I'm doing exactly the same as I've been doing in the previous slides, which is, I'm trying to show you this because basically an example like this, it will come in your exam, and I want to let you know how to solve it. Now, this is the condition that it will receive something again between 0 to 3 units of water. How much water it will receive? So it will receive exactly the same, it will receive this exactly water in excess times the share of user number 2. So the water in excess, as we were discussing it before, is this Q in minus the Q river plus X3, and this will be times the share of user number 2. And in this case, number user 2 will be their water demand divided by this the sum of x1 plus x2 demands. So think about this. So the water in excess will be divided equally, and in this case, user number 1 will that water in excess will be allocated to it in the ratio of 2.5 over 5.5, and the user number 2 will have that water in excess in the ratio of 3 over 5.5. So that's how they will be able to divert water. Hi. So let's start. Let's get going on part number 2. So basically, what we're going to be doing is first fill in this table, and once we have filled in this table where is the water allocation for a river user 1, 2, and 3, then we're going to be also filling this part of the mass balance model. Okay, so for this first part, the first thing that we want to do, that we have to do, is define the name of the different variables. So these are the variables that we have in here that we're going to fill. So you will have to go to these formulas, define name, and basically what we're going to be doing is select this C54. So once you have done that, this variable, we're going to call it river underscore WD, water demand. We're going to save it in this sheet that is part 2 river, as it is instruction in us here, and it's already C54. So when I do that, as you can see, this one now is the name of the cell is not like this, that is D54. The name of the cell is actually river underscore WD. So we're going to do the same for the following 2 others. In this case, it will be X1 water demand WD, and we're going to save it in this part 2 river sheet. And then we're going to be doing the same with this X2 underscore WD. Again, we're going to save it in here in the river. And finally, we're going to be doing the same with this one, X3 WD. So we have now saved these variables in here. Notice that when you click here in this name manager, it actually comes the different names of the variables that we have just created. Now we will start in this part, in this first part, and basically what we're going to be doing is defining, as I was explaining before, how the river will use this first water, which is this is that specific equation. So for us to do this equation, basically what we're going to be doing is first saying that if the available storage is less than the less than the river water demand, then it's going to be only this available storage. So this portion here is this portion here. Now the following one is this one that is in the middle here, which is basically that if the available storage is if this available storage is the river plus the sum of x1 plus x2 plus x3, so if basically if this available storage is greater than this, then what we're going to be doing is using this, which it will be, so basically this is this last part. When you're saying that the available storage will be 2 plus would be the value of the river plus the sum of all the different water demands, demand 1, 2, and 3 for x1, x2, x3. So when that happens, so if this available storage, if this is greater than the river plus the sum of all of them, then it will be this value, this available water minus this. And this is when the river has more water than 2. Otherwise, so we have done this, we have done this, otherwise it will be 2. So that's what this says. These are the values of the river, as you can see here. Then what we're going to be doing is now estimating the water allocation for user number 3. So for this part, basically we're going to be following this. So the first part is this. So if Q in is less than 0, then it will be 0, which is this portion here. If the available storage is less than 2, then it will be 0. Why is that? Because, I mean, all that water will be used by the river. Then the second portion is this, which is basically that if the available water is greater than 2, is greater than the river, and comma, the available water is less than 7, which is less than the river plus 5 units of the user number 3. So if that is the case, then it will be this Q in minus river. So the available water that is above once the river has taken its water demand. Otherwise, it will be 5, which is what is going on here. So basically, that's what we have in here. And then this will be the estimating that specific all those values for now user number 3. Now let's take a look at user number 1. And in this case, for user number 1, basically what is going on here is that this first portion is that if the available storage is less than 7, so if the available storage is less than the river plus the value of water demand number 3, that will be 0, which is that's what is going on here. The second one is this middle if statement. So if the available water minus the river plus x3 is greater than x1 plus x2. So if this value is greater than x1 plus x2, then it will be 2.5. And that's what is going on here. If this available water minus the river plus x3, if this one is greater than x1 plus x2, then it will be 2.5. Otherwise will be the available water, which is Q in minus river times xd3 minus the water demand of 3 times the proportion, which is the demand of x1 divided by the demands of x1 plus x2. So basically that's what is going on here, and that will be how you can allocate water for x2. Now let's actually take a look at x3, no, excuse me, x2, which is the last one that we're just missing here. And this will be for x2, okay? And this is exactly the same as the previous one, but basically what we have different here is that here it will be x2 as it is mentioning here, and in here is x2, the water demand for x2. So this will be the water demand allocation for x2. As you can see, once we have passed this 12.5, which is the sum of all the different water demands, which is the sum of these water demands. So when you're seeing this sum is when we have 12.2 units of water available, then everyone will get 12.5 or more, everyone will get their water demand. Okay? And now what it happened is that we have to, now we're going to this part 2. And basically you can do each of these two methods, method 1 or method 2. I'm going to select method 1, which basically what I'm going to do is just copy this first row, and I'm going to paste it in here. And that will do it. That's how I will be able to use this kind of mass balance model to estimate the water demand in here. So let me just okay. So this is what we're going to be doing here. So if this is 14, so basically here everyone 12.5 will be divided throughout, and that 1.5 that is remaining will get to the river. That's basically what is going on here. So in the instance of 11, so this guy gets 2, this guy gets 5, and then the remaining of the water is divided proportionally to these two guys here. Now in this case, for the last when we have 0, no one gets any. When, let's say for instance, when there is 7, so only these two guys will get water, but they will not get any. So we have 5, this get 2, this get 3, and these two guys get nothing. So you can actually see how this is working. So when we have 9 units, so this river gets 2, this gets 5, and then the remaining, those 2 units is divided 0.9 to x1 and 1.1 to x2. And they are basically, they have exactly the same share. So if you think about that, if you divide this over this, they are actually receiving the exact same proportion, both of these users. In this case, it will be, see, both of them, they are receiving the same proportion, which is 36%. Okay, now something that you can actually see is this dashboard. And basically what is going on in this dashboard is that you can see who is receiving water. So these are the inflows. You can see that the river pretty much received all the water except on this 2023, where it didn't receive any water. Similarly, user 3, only 2 times they have a water supply deficit, so water was not delivered in its full amount in these 2 years, 2023 and 2038. You can see that users 2 and 3, they follow exactly the same pattern. And this is because their water is allocated proportionally. But you can see that they have a lot of water shortages throughout the time. So now what we have done is a little bit more of a qualitative way of addressing water supply, but I think we can do it more quantitatively. And in this case, it will be through using some performance criteria. Some of the ones that are more widely used are these 4, which is reliability in terms in time and volume, vulnerability and resilience. And I'm going to explain you how you can obtain those. So reliability, it comes in 2 flavors. So the first flavor is how often a water demand is fully supplied. So how often in time. That will be if, for instance, in this case, we know that there are 21 years. So these are 21 years that we are doing this analysis. And in this case, in 2 years, they didn't receive any water, or it wasn't fully supplied. So in this case, the reliability, it will be 19 over 21. So on 19 years, it was fully, their water supply was fully allocated, its water demand was fully allocated, which that represents about 90%. So that's basically what it is. In this case, it will be 20 out of 21, which is 95%, and so on. So that's basically what we're going to estimate here. In this case, what you can see here is that in order to estimate reliability, basically we need to build this matrix of deficits. So how can we estimate this matrix of deficit? So basically, we have to subtract the water demand versus the water supply. So if the water supply is equal or greater than the water demand, then there was no deficit. Otherwise, you subtract the water demand minus the water supply, which is basically what I'm saying here. So if this is greater than this, then it will be, then so if this value is less than this, then you will have to subtract them, this minus this. Otherwise, it will be 0. And that's what is happening in here. So that's pretty much what you can see from that we have already knew from our analysis, that in 2023 the river didn't have a fully water allocation. Okay, now the next thing that we will have to calculate is these different variables that it will help us to estimate reliability, vulnerability, and so on. So the first one is to count how many years do we have in this period. And in this case, basically what we're saying is counting the number of times that we have a number here, which is 21. So that's the number of years. Then in the next one, what we want to estimate is the number of deficits. So we know that there is only one deficit in there. And basically what we're saying is that in this vector, in this group of cells, how many they are greater than 0. And basically it's just 1, and we can see it in here. Then in this following one, we're going to estimate the number of years that we didn't have any deficit. And in this case is the same on this group of cells, on this vector, estimates the ones that are equal to 0. And in this case are 20. So 20 plus 1, it will be 21 there. The next one will be to estimate, if there is a deficit, to estimate the sum of the deficits. So how much water, what was the total of the water deficits for that specific water demand? And in this case we know it's only 2, because that's the only one that it did happen. Then we're gonna estimate the sum of the water demands. And in this case, so how much water was requested, was demanded during this 21-year period is 21 times the water demand for a river. So that's the total during those 21 years, the total water demand. Lastly, what we're going to estimate is what was the water supply, the sum of the water supplies. And that is pretty simple, because basically it's this sum of the water demands minus the sum of the deficits. So that's how much it is. So again, in order to estimate the reliability, basically it's the number of times that we didn't have any deficit, that we know that those are 20. So 20 times we didn't have any deficit, and the total number of times, so that's what we have in here, the total number of years is 21. So it has to be 95%. So basically how can we estimate it in here? Well, basically, that's how we can estimate it there. And yeah, that's correct. It's 95%, as we have just kind of estimated in parallel. Now the next one is the volumetric reliability, and basically relates how much water was supplied compared to the total water demand. And in this case, this one, it will be this over this. And that is also 95%. Then vulnerability expresses how much water is, so when you have a deficit, so this deficit of 2, so it estimates the average of the deficits. So if we have more than 1, we will estimate the average. And once you have estimated that average, then you will estimate how that average compares to the water demand. In this case, the average of this time series is 2 because that's the only of the average of the deficits is 2. These are the deficits, only 2 that are occurring here. And 2 over 1 is 2, so that's the average. And then if you divide 2 over 2, which is basically the amount of how this average deficit is compared to this water demand, then in this case it will be 100%. 2 over 2 is 1 or 100%. So basically that's what we can do in here. It's basically what is saying that it was, what was the average of the deficits, the sum of the deficits divided by the number of times that you have a deficit, that's a deficit, and that value divided by the water demand. So you express it as a percentage of the water demand. And that's what is going on there. The problem about this is that vulnerability, it does has, so if you don't have any deficit, then when you try to divide 0 over 0, it's undefined. So basically what we will have to do in here is say that if you have no deficit, then the vulnerability will be 0. So you have no vulnerability, there is no deficit, so the average of the deficit is 0. Otherwise it will be that the average of the deficit, so the sum of the deficits divided by the number, you get the average, and that divided by the water demand, which is here, which is in here. Okay, well, so that will be for this. Now the resilience is, it estimates when the system fails, how fast the system recovers. What is the probability that the system recovers? So for this, basically what we have to estimate in here is, so the first column in here is zeros. But basically what we want to estimate in here is flag when the system recovers. So basically what we're going to be doing here is flagging when this year was 0 and the previous year we had a deficit, it was greater than 0. So basically that's what it's saying here. If this is equal to 0 and the previous year is greater than 0, then write here a 1, otherwise it will be a 0. So when you do that, as you can see here, basically on this year is when that condition applies. This is 0 and this was greater than 1, greater than 0, sorry. So this is the time when the system recovers. So we're going to be counting how many times the system recovered to the number of times that it was in a deficit. So that's how you can estimate it down here. Now similarly, so that's how you can estimate it in here, okay? Which is that number of dividing the number of times that it recovered over the number of times that you have a deficit. So when it failed, it recovered. So there is 100% probability that the system will recover. Now, because if you don't have any, again, any deficit, in theory, your system is 100% resilient. What that means is that it hasn't failed. So in this case, that's when we are saying if this value is equal to 0, then it will be 100%. Otherwise, you will have to divide this over the number of deficits. Now, here what we're going to be estimating is so with all these numbers, you can see that we have 95, 95, the is very vulnerable. So it will get into problems, but it's very resilient. So how do we know that it's this performance is good or bad? So in order to do that, you develop some index or indices, which basically what they do is they aggregate all the values into one. In this case, what is going to happen, or what we're going to be using, is this water resources sustainability index, which is the geometric average of all of these guys, which is what is explained here. Because there are four, basically you're going to be multiplying. So this is a geometric average. You don't add and divide it by the number of n. When it's a geometric average, you multiply all of them and then elevate that product to the power of 1 to the number of elements. In this case, if we have 4 elements, 4 criteria, it will be 1 to the 4th. If they were 3, 1 to the 3rd, or 1/3. If they were 2, to half, and so on. So notice that reliability and resilience, because they, so if all of them they were 1, you want to get the highest number, or the number closest to 1, that will represent a better performance. Reliability, you want to have 100%, the same reliability in volume 100%, the resilience, that the system recover really fast, 100%. You want to have here a 0 vulnerability. And when this happens, so basically what you have to do is 1 minus the vulnerability. So if the vulnerability is 0, this value will be 1, and if all of them they are 1, when you do this 1 times 1 times 1 times 1 to the 1 to the 4th, that will be 1. That will be 100%. So in this case, for this one, basically it will be what I mentioned, which is the geometric mean, which is these two reliabilities and the resilience multiply, and then 1 minus the vulnerability to the 4th, and in this case is 0. What that means is that the system is very reliable and very resilient, but so the water supply for the river is very reliable and very resilient, but when it fails by 100%. It really crashes. So that is not sustainable. Let's try to do the same for. So that will be it for this part. Then you will have to estimate the same water, the same performance criteria, reliability, resilience, vulnerability for the rest of them. And in order for you to do that, basically you will have to follow these instructions, and then you will have to fill or to respond all these different questions. In this case, for instance, if you want to obtain the same for the rest of them, so what you can do is, in this case, do something similar, but instead of river, this will be x1, and here it will also be x1. That's how you can estimate. So this will be comparing these two. And then you can do it for the rest of them, considering that this will be x2 and this will be x3. So basically what I'm doing here is making sure that I have these values here, that I am using the right, and basically here you can see that, for instance, for x3, it only has 2 deficits in 2023 and 2038. And we have already seen that x1 has this big deficit in here and this big deficit in here. Now, once we have estimated that, we can also estimate this matrix of resilience, okay? And basically in the matrix of resilience, we can make sure that this is also working for all of them. So here just noticing that when it fails in the following year recover, so that's why we have here a 1, here the same. When it fails, it recover. And this will be the same. When this period of time, this is until it recovered. This is the same here. It failed, it recover, it failed, it recover, it failed, it recover, and so on. And we can estimate this. And basically, what we're going to be doing here is, yeah, there is still 1. Here we have 11 with that had a deficit. In this case, 10 that didn't have a deficit. The sum of the deficits is the sum of that vector. Here it will have to be 21 times x1 water demand, so 21 years times the water demand of that, and then this will be that difference. Here we can copy all of this, and I think everything will be fine until here, because this one has to be x2 and this one has to be x3, which is the total water demand, which is multiplying the water demand times 21 years. So that's what we have in here. These are the sum of the deficits, how many times. Notice that they have the same number of deficits, which that's by design. So if there is not enough water, they will share the deficit in the same proportion. Then we're going to be here working on, for instance, the reliability, which is this. This will be the reliability in volume. The vulnerability, in this case, it has to be divided this one by x1. The resilience is okay. This will have to be divided by x2, and this will have to be divided by x3. The rest we can just copy and paste it. So as you can see, this is pretty interesting. So user number, so these are the users. So here we have so river, user 1, 2, and 3. Notice that, for instance, in this case, these two have the same performances, and that's by design. Remember that we said that they have the same priority, so they will have the same performance. This guy has a higher performance, and why is that? Because, well, it's a senior. 90% of the times the water, its volume was delivered. 90% of the times the water demand was fully supplied. The volume is 93%, so basically it was supplied 98 out of 105 units of water. The vulnerability, when it happens, so the sum of the deficit is 7. 7 divided by 2 is 3.5. And 3.5 compared to 5 units of water, which is the water demand of this, is 70%. When it failed, it recovers, so it has a high. So this is why it has this performance. So basically that's this for this part of the for the exercise. Take care.